We will get started. This is the new project initiative. The title is 5G mmWave Permittivity Reference Material Development. As I mentioned, my name is Urmi Ray. I'm the mmWave project lead for iNEMI. This is my contact information for contacting me with your interest in joining the project. But let me just go ahead and get started with what the project is and about. So as I introduce the co-project leads, they are the brains behind this project. We also have initiative team. Let me just go through again, reintroduce Dr. Nate Orloff from NIST and Dr. Michael Hill from Intel, who have put together most of the material. And then we also have a very active initiative team that have been really fundamental in producing the requirements and driving the content behind some of the work that we've already done on this initiative. And though that team includes Intel, ITRI from Taiwan, Keysight Technologies, NIST, as we already talked about, Nokia, and QUED. There are others also, but these are the primary project initiative team. And what we have here is the problem statement, which I hopefully I'm assuming that most of you would resonate, no pun intended. So for millimeter wave applications, we have things like permittivity and loss tangent are obviously the key material performance metrics as you design and implement the low loss millimeter wave applications and products. What we have had for the last 2 years, actually, since June of last 2020, is a very active global industry team that consists of 26 members that have been coordinated by iNEMI that have been addressing this problem for the last 2 years and really have looked into the problems of accurately measuring and characterizing low loss materials. And an extensive round robin experiments for this performed by a group of this industry team has shown that even with well-trained labs and well-trained personnel, there is sometimes more than plus or minus 2% disagreement in the measurements, the permittivity and loss tangent measurements for the same material sample. And even though you may think that this is a good number, but really, if you want to get to the accuracies you need to for very high performance type of applications, next generation filters and antennas and things like that, you would need something much closer to 0.2% or less than 0.5% uncertainties to improve the metrology capability and overall acceptance testing. That is really the feedback from this large industry group that have been participating in the previous project. And you can really see the work. This is just from the previous project, the 5G materials characterization project. What you see here is that even though you have a generally a good agreement, but we really need to do better in terms of metrology. And one of the big problems or issues, the gaps that we've identified is that there are no traceable permittivity reference materials for any of the frequencies that we are looking at or the industry is looking at, whether it's for current 5G, which is 40 gigahertz or lower, or what the 3GPP group is looking into, which is the 6G implementation, which is which could be hundreds of gigahertz, right? So there is a discussion about the need for traceable permittivity reference material spanning the millimeter wave frequencies. And we believe that there is a big benefit for the different industries that are working in this area. So that brings us to this new project. We have conceived this new project based on the industry needs. It's a collaborative, pre-competitive R&D project, and this is the subject of the discussion today. So this is the subject for the call for participation webinar that you're all attending today. So give you a perspective what we are looking for or what we're planning to do, and in terms of timeline, roughly it's a 2-year type of timeline that we are looking at. The output is industry standard reference material that we can all be that is certified, and therefore it's something that will provide all of us with traceable and accurate reference for permittivity measurements for millimeter wave. So what we believe is the way we have organized is that we have the first deliverable is the first proof of concept construction. And then we will have, and this is the benefit of an industry collaboration project, that we can then utilize this proof of concept material. It's an artifact that can be used in round robin testing to validate the first round of accuracy and handling and data collection accuracies using this type of the first proof of concept. In addition, we will have the dimensional and traceability analysis that has to go hand in hand with the POC construction, the proof of concept construction, and then we will continue that. We might have to iterate on the second round of the proof of concept. That's what is planned in the second year, roughly spanning into the second year. We have in parallel some multi-lab testing of the second proof of concept, and then the tests associated with it, culminating in the end of the project with validation of this material, the standard reference material. Okay. And then the status today is that we have actually performed a fair bit of initial testing for the pre-proof of concept that was done as part of this previous iNEMI project that I'm referring to, the 5G materials characterization project. This was critical to get some early information about how to go ahead and plan for the proof of concept tests. We also have the ability or confirmation to have the critical resources from NIST that we can allocate, or we can not allocate is not the right word, but who can support this project, because this would be driven by National Institute of Standards and Technology, with Nate being the champion from that team. We also are going to use Fuse Silica as our primary candidate, and we have been working with the source as well as a methodology of preparing this material with very, very low TTV. We have the partnership with Mosaic Microsystems, who I believe is also on the call, to be able to supply the material and be able to process the material for our the rest of the project study. And then because this is a normal question that is asked by everybody who is new to joining a project with iNEMI or any other cross-functional project. What do we expect from the participants here? So we have an active working group that will continue, and we can add to this working group. This group is the brains. We not only do drive the the technical aspects of it, but they also perform some of the round robin proof of concept tests. This working group will meet biweekly or monthly in technical meetings as needed. From a full group perspective, we believe that frequency is monthly updates, obviously getting feedback from all of you as to the requirements in a large group basis that are monthly, that are planned monthly. So from a project participation perspective, this is the timeline that we expect. And again, we invite you all to join this team. Please contact me as soon as possible. And for those of you who are not familiar with iNEMI, I'm going to spend literally 5 minutes to just give a brief introduction. It is an R&D not-for-profit organization, pre-competitive, driving collaboration within the industry on key items and topics that is valuable to basically the electronics industry. And the value of the membership to iNEMI and participation in these projects is that you have access to iNEMI roadmap that is under construction right now. We had put the roadmap activity on hold for a year or so, and we are revamping the roadmap effort. You'll hear a lot more about it. You have engagement in the iNEMI projects. That is really what I believe our members value in terms of cross industry, cross functional collaboration to influence the research and development directions. And then, of course, the ability to leverage the iNEMI network. A lot of our project members really value the ability to work across the aisle and leverage the learnings as well as collaboration, even amongst competitors, because we are all working on areas that are pre-competitive. Just a couple of examples. We have tools, we generate best practices, test methods, a lot of characterization. These are some of the key items from the last year's projects. This is an industry test method driven by the 5G materials characterization group. We have a lot of projects in looking into smart manufacturing, characterization of solder joints, certainly tools for inspection and metrology for packaging, photonics areas, sockets, etc. And then a couple of examples, and you'll get this package of information since you've joined the webinar. So I won't go through this, but this is the 5G mmWave materials assessment project that I talked about. There's a similar project, kind of a sister project, looking at the impact of copper, roughness of copper foils for 5G applications that my colleague Steve Payne is leading. Some of you are participating in that project. And then one other example, kind of in a slightly different area, which is on substrates and looking at RDL adhesion strength measurements. I just picked a couple of examples. There are currently, in any given year, there's generally of the order of 15 to 20 active projects. Typically, we try to manage these projects in a pretty short time window, 18 to 24 months. And then so that we have an active group working with a pretty aggressive timeline. And we believe that's the model that is successful and is appreciated by all of the industry members that we have. By the way, iNEMI also has a lot of, I keep talking about industry, but we obviously work very closely with the national labs and across the globe, and a lot of partnerships with the universities. Okay, so that's the introduction part of the talk. I'm going to hand it over now to the tag teaming team of Nate and Mike. Most of my understanding is that we will go through now the technical details, and I'll hand it off to Nate.
Great, thank you guys. Pardon me. Thank you guys so much for coming today, and thank you, Ermi, for the introduction. You guys are all here because you're part of the semiconductor manufacturing complex and around the world. You're already familiar with the fact that the semiconductor industry represents a huge part of the global economy. And I think we've listened to you and heard you about what your needs are. Go ahead, next slide. So in a recent 5G iNEMI report, it pointed out that the lack of traceable reference materials for millimeter waves is a very serious problem. And this lack makes verification of measurement methods and laboratory techniques impossible in an industry setting. Adding to that, an SRC report also identified the needs for new dielectric characterization techniques above 100 gigahertz and up to 500 gigahertz, and the need to characterize inhomogeneous and anisotropic materials for industrial applications. So we know that dielectric properties impact all of microelectronics and manufacturing, and we've heard you about what you need from NIST. So go ahead, next slide. So a lot of this was borne out by the fact that some of you went to the NIST Standard Reference Materials website, typed in the word dielectric to order a new standard reference material, and you found that, go ahead, next slide, that there is no standard reference material for dielectric constant, regardless of the frequency, whether or not it's DC or AC or millimeter waves. There's just no standard for dielectric constant and loss tangent, and that impacts your bottom line because it impacts internal metrology characterization and acceptance testing. Go ahead, next slide. So how do you guys use standards in your everyday labs and materials and device development? Well, one of the ways that you use them is a metrology capability analysis. In this case, you might have 3 technicians, Paul, George, and Joe. They all measure the same thing, and 2 of them get a different answer. In this case, you actually don't know who is right. You might think that obviously Paul and George, because they got the same answer, they are actually doing things correctly and are actually getting the right answer, and Joe is getting the wrong answer. But it could also be that Paul and George are wrong and Joe is right, and there's something fundamental in their metrology or in their calibration, and you wouldn't be able to identify that problem without a standard reference material. So the second application for standard reference materials is the acceptance testing. Go ahead, next slide. So in acceptance testing, you're a vendor or you're a manufacturer, and if you're a vendor, you want to provide the most accurate specification for your material. You want your specification to be NIST traceable so that you know that it's right. And then when you want to send it to your manufacturer, you want them to implement that permittivity value or loss tangent value that you provided into their models so that they can do, when they do internal testing, they also get the same answer, right? So it creates trust between manufacturers and vendors. If you're a vendor, if you're a manufacturer and you're receiving a material, you want to know that the materials that the vendor is providing and the specifications that they're providing are correct. In this case, we have a manufacturer and a vendor, and they both are providing the manufacturer is providing a specification of permittivity 11, but the manufacturer measures a permittivity of 10. Now, this difference is only 10%, and you might not think that that's a really big deal, but as Ermi pointed out, industry really needs uncertainties on the order of 0.2%. And obviously, this is unacceptably large deviation between the vendor and the manufacturer. So without a standard reference material, industry can't perform these fundamental tasks in order to make new technologies. Go ahead, next slide. So what can happen without a standard? So when Mike was first telling me about his problems and what he does at Intel, he gave a really good example about the capacitors in the back of a CPU. In this case, what Mike said was that if the permittivity is wrong by about 10%, just like our earlier example, then that might require them to include 4 additional capacitors on the back of their CPU. Those additional capacitors would cost a total of 34 cents per CPU, but over 100 million units, that would cost Intel about $34 million a year. Now, that's an unacceptably high cost that Intel could have avoided, or in this hypothetical example, they could avoid if they had a standard reference material to calibrate their measurements. Now, this is just a hypothetical, but it illustrates the point that when you have high volume manufacturing, getting the permittivity right is really important. And that's also true for the loss tangent. Go ahead, next slide. So that's even more true for next generation computing, which requires heterogeneous integration. In these types of circuits that are heterogeneously integrated, that's the bottom right there, you have many, many layers of different dielectrics that are integrated vertically and die bonded together. And all of those materials need to be characterized at a whole variety of frequencies. You have input-output signals that have signal information in the high gigahertz and the hundreds of gigahertz. You have DC signals and capacitors, and all of those materials need to be characterized in order to get the performance that people want from their devices. Go ahead, next slide. So industry needs reliable material properties, and 5G really extends beyond, oops.
Yeah, sorry.
That's okay. 5G really extends beyond just materials characterization. It really impacts automotive radar and industrial applications that go well beyond what we think of as just telecommunications applications. For instance, you might be surprised to know that that automotive radar is one of the leading sectors for companies like Keysight and vector network analyzer manufacturers because they need to characterize the materials that go in automotive radar. So that's really important. Go ahead and chime in. That sounds great, Ermi, if you'd like to take this slide. Okay, we'll go ahead and do the next slide. All right, so how can we fill this? So we've already made the argument for why traceable materials are important, how they impact your bottom line. So you know that you need them, but you don't know what they are. And we also have this fundamental problem of we need to get from the fact that we don't have a standard reference material to a new place where we do have a standard reference material. So how are we going to go from the left to the right? And that's what this iNEMI initiative is going to do. So we have some ideas about what those steps are. So it starts, go ahead, next slide, by defining what the materials and the methods are that we're going to be using to develop a standard reference material. In this case, a previous iNEMI report talked about fused silica, and we're going to discuss that in a minute. It also identified split cylinder resonators as a possible traceability path. We're going to talk about that as well. And go ahead, next slide. The next step is to develop the fundamental theory that's associated with the standard method that we're going to be using. Then we're going to be measure the scattering parameters of our devices with and without the sample. That's going to allow us to extract the material properties once we've extracted the dimensions. So we're going to talk about each of these steps one by one and explain how you, as an iNEMI participant, can play an essential role in defining what the next generation of standard reference material is and what it looks like. Because NIST doesn't want to just make solutions that fill a traceability gap. We want to make solutions that solve problems that matter to you and impact how you would use them. Go ahead, next slide. So let's talk a little bit more about step one. So here, the iNEMI special report identified fused silica as a candidate for a next generation standard reference material. That's for a few reasons. One, we're able to manufacture it into this geometry, which is this rectangular coupon with the rounded edges. It's easy to manufacture in that geometry. We can also get it to have these very precise thicknesses. In this case, we've got a target thickness of about 150 microns. And we can hit total thickness uncertainties of about 0.5 microns, actually a bit better than that. About 100 nanometers, thanks to Mosaic's new processes. That total thickness uncertainty might sound sort of unbelievably high. You might think, wow, that seems like a really, really low total thickness variation. That isn't that overkill? And the answer is no. We actually need that level of uncertainty on the total thickness variation in order to hit that specification that Ermi talked about, which was that 0.2% uncertainty on dielectric constant and loss tangent. So in order to deliver that types of uncertainty to you, we need to do much, much better, and that's what's required. Would you like to pipe in, Ermi? Okay. Okay, so the next step is to choose a method. Now, there are many different materials characterization methods, and we would love to develop all of them, and we hopefully will eventually. But we've decided to start with the simplest possible method, and that's the split cylinder resonator method. And it looks really, what's really nice about this method is how it works. So you're just going to connect your vector network analyzer to the input and output. You open up a slider, that's this little piece on the backside right here, and you stick your sample in. That's that blue little coupon that goes in. And so what's nice about this technique is that it potentially has a very short traceability path, where the only thing that we need to measure is the diameter of the cavity, the depth of the cavity, and the dimensions of the sample. And go ahead, next slide. So the technique's pretty simple. The way that it works is you just close the little connector, and then you measure the cavity with no sample. Then you stick the sample into the cavity and close the little clamp, and then you measure it. And this is just a cross-sectional view of what the cavity looks like. So here what I've done is I've cut the cavity in half so that you can look at how the sample sits inside the cavity. And so we're going to explore other candidate paths as well as a part of this iNEMI initiative. And we want to include whatever path you're doing in your lab as part of the characterization and development of this next generation standard reference material. We want to develop a solution of that little blue coupon. We want to make sure that it works for you. Go ahead, next slide. So there are many different types of materials characterization techniques. I've already talked about SCR. There's Fabry-Perot resonators. That's particularly attractive for things like automotive radar and millimeter wave communications and space satellite communications. That allows you to characterize the anisotropic in-plane permittivity. It's a fantastic technique, and we're fortunate to collaborate with Qued and Keysight on their solutions for that technique. And then the other technique that we're interested in is balanced circular disc resonators. The drawback to that particular technique is that you need two identical samples. That can be difficult when you have total thickness variations that are different for different samples. So ideally, you'd have the same identical sample, and that would improve the accuracy of that technique. So we're probably going to start with SCR, then we might develop either FPOR or BCDR next. But really, your input as an iNEMI participant will help us decide which thing we're going to focus on and how we're going to prioritize the theory and the uncertainty analysis that goes into making each of these techniques traceable. But to start, we're planning on starting with split cylinder cavities because it's definitely the simplest. Go ahead, next slide. So theory is a major part of the traceability chain. Nobody likes looking at math, and this isn't even the right math for the split cylinder cavity. This is something called Slater's perturbation equation. It's in your book on electrical engineering. It's probably a chapter about this. But the key point is how we use equations like this. Go ahead, next slide. I didn't show you this SCR actual theory because it's particularly unpleasant to look at. But there are key features that you can glean from this equation, which is pretty close, to understand how the things that we measure and the things that we know factor into the permittivity measurements that we want and the uncertainties. So let's talk a little bit about how you can reduce this equation. So at the end of the day, you're going to take this equation, you're going to solve it, and you're going to get these two blue boxes on the left and the right. So on the left side, you can see the real part of the permittivity of the sample, and there's two key parameters here. There's the frequency shift due to the presence of the sample. So that's how much the peak moves with and without the sample. There's the volume of the cavity, and then there's the volume of the sample. So the red things come from dimensional metrology, and the blue things come from fitting S-parameter measurements that we'll talk about in a second. And to get the imaginary part of the permittivity, which is part of the loss tangent, we're going to extract the quality factor of the resonance properties of the cavity. So go ahead and go next slide. So when we measure the split cylinder cavity, the way that we do it is with a network analyzer. If you're unfamiliar with that, you can think of it as just a thing that's sending a signal from the left through that black cable into the cavity, and it's resonating like a note on a guitar or a harmonic on a guitar. And then at that resonance frequency, a signal can propagate from the left to the right back through that black cable up to that vector network analyzer. And that allows us to measure the transmission through the cavity. And by measuring the transmission, or S parameters, through the cavity, we can find what the resonance frequency is and the quality factor. And we're going to talk about, as when you're a member of the iNEMI initiative, your input will help us test the usability of the candidate SRMs in your manufacturing test measurement setups. Go ahead, next slide. So what does that mean? What does it mean to measure the S parameters of a cavity? Well, we're just going to measure the transmission through the cavity as a function of frequency. So here what I'm plotting is the transmission through the cavity as a function of frequency. That's the yellow curve right there with the black line through it. And on the right-hand axis, I'm plotting the phase through the cavity. So when you have a resonator that's a little bit below resonance, you have a positive phase shift relative to the resonator. That's what you're seeing in the orange line right there. And then as you go through resonance, the phase shift relative to the resonator is 0. And then as you go a little bit faster than the resonance, you get a negative phase shift. And so you can see that there's a peak in the transmission at the resonance frequency. And all we're going to do is we're going to measure that resonance frequency, that free FC and QC. And sometimes we'll write the word omega C. That's just 2 pi times FC. That's the angular frequency right there. So we're just going to measure the cavity with and without the sample. Go ahead, next slide. So let's take a zoom out here. We're going to zoom out and we're going to look at the cavity. You can see that it's a very, very sharp peak without the sample. Go ahead, next slide. Once you introduce the sample, the peak moves to the left and down. That's because you're kind of like loading the capacitance in the cavity, and it's kind of like an LC circuit. So as you increase the capacitance, that's inversely proportional to the resonance frequency, and so it shifts down. So we measure how much it shifts down. Go ahead, next slide. So we measure how much it goes down and how much the quality factor changes. So here you can see that our resonance frequency is shifting by about 1.5 gigahertz, and the quality factor is changing by about 2,500. So these are essential inputs that go into the theory and allow us to extract the material properties. Go ahead, next slide. So the next thing that we need to do is we need to measure the thickness of the sample. That's one of the most critical properties of the little blue coupon, right? And we think that this white light interferometry technique that's being sold by FormFactor is the best way to measure the thickness of that coupon for our technical applications. And in this case, we really need uncertainties on the order of like 100 nanometers, and you'll see why. So there are a lot of requirements to this technique. We're still learning about it. And what this technique would allow us to do as your participation in the iNEMI activity is you would be able to compare our measurements of the thickness of the sample to which is calibrated with NIST standard reference gauge blocks to whatever measurement technique that you're using. So you can also view this standard reference material as also a thickness standard for measuring glass, which is kind of interesting. Go ahead, next slide. So we need to measure. Now, I said that this technique was something that we thought was the best measurement technique. We're interested in learning if there are other better measurement techniques. The key metrics for using this measurement technique are to know that you have to measure from both sides. If the material has some warp or bend in it, then you need to be able to measure that thickness accurately, right? So if you're only measuring from the top, and you can imagine that the material is cupped, then you might convolve the shape of the material into your thickness measurement, and that might perturb your results. So you really need to measure from both sides. The next problem is that your material might have surface roughness. So if your spot size of your materials, of your dimensional metrology technique is large compared to the surface roughness, and the surface roughness is high, you might convolve that surface roughness into your thickness measurement, and that also might impact your permittivity extraction. The next problem is that you can't assume material properties to get the thickness measurement. This was a constant thing that I was talking to different vendors about when we were trying to find the right technique. They were like, oh, you can just use ellipsometry, right? But that assumes the index of refraction to get the permittivity out. We can't do that. That's not allowed. You can't use the thing that you're trying to prove to get the thickness. That means that your number is circular, right? Your logic is circular. So I don't really care what measurement technique we need, but we do need uncertainties of less than 100 nanometers. Go ahead, next slide. So the final part to getting traceability is that the dimensional traceability of the cavities. So this is a really big piece, and I'm really happy and proud of my management for really coming to bat and getting NIST Gaithersburg to help us get these measurements. As you might imagine, dimensional traceability is one of the most highly sought after and demanding things that NIST does, right? The people that provide dimensional traceability are working all the time to provide dimensional traceability for everything that you can possibly imagine. And so these people have agreed to, NIST Gaithersburg has agreed to dimension our split cylinder cavities as a top priority for the next fiscal year. And we're going to talk about what those dimensions mean. Go ahead, next slide. So the way that they do these dimensions is with a very special coordinate measurement machine. And this might look very different than any coordinate measurement machine that you might have seen before. This is a very special one that NIST had made for this exact purpose. And it's capable of providing uncertainties down to 70 nanometers at multiple points along this cavity. So we're going to get the dimensions of this cavity, we're going to get the diameter and the depth of the cavity, and those measurements and their associated uncertainties factor large in the total uncertainty on the permittivity and the loss tangent that we will provide to you. Go ahead, next slide. Okay, so now we've talked about this pathway, and I told you all the steps in the pathway, and we also have prototypes that we've begun to do testing at NIST and characterization techniques, and so we're well on our way to providing traceability, maybe within the next couple of years, right? Maybe within the next year even. And at the end of the day, you really want to know how those different inputs factor into the total uncertainty that NIST can provide to you. Let's go ahead and go next slide. So at the end of the day, we really want to know that NIST solution is a solution that impacts you and your needs as industry. And there are a couple different things that you need to keep in mind, right? You need a total uncertainty of about 0.2%. Well, there's something called the gauge makers rule, and the gauge makers rule means that if that the gauge that you use to make your measurement needs to be about many factors smaller than your total uncertainty on your gauge. Does that make sense? So if you're providing a specification that is a 0.2% uncertainty, NIST needs to provide you a standard that has many times smaller total uncertainties, typically about a factor of 10. So NIST's goal uncertainties should be about 0.02% on the total uncertainty on the permittivity that we provide to you. Now, depending on the applications, you might be able to tolerate a gauge maker's rule of about a factor of 4, and that's what this plot is here. Let's go ahead and do the next slide. So the key things to understand this slide are that the y-axis is the total percent uncertainty in the dielectric constant on the SRM that we're providing to you, right? And the orange line here is the uncertainties from fitting the S parameters. That's how accurately we know the Q or how accurately we know the resonance frequency. The green line is the uncertainties due to the dimensional metrology. And so the bright green line, go ahead, next slide. The green dot is the total thickness uncertainty in the wafer that we would be getting from Mosaic for the fused silica SRM, and the blue dot is the uncertainties assuming a 1 micron dimensional uncertainty on the cavity. So you can see how these different numbers factor into the total uncertainty that NIST can provide to you. I'm not really worried about the S parameter fitting right now. the contribution of the uncertainties on the S parameters are so small that they almost don't matter at this point. Like NIST has crushed that. S parameters, no problem for NIST. But dimensional metrology, that still looms large. So what I don't want you to think is that this is exactly the plot at the end of the day. I've made a lot of approximations to make this plot for you, but it provides some idea about how the total thickness uncertainty in the sample and the uncertainty in the cavities play into the uncertainty of the dielectric constant that NIST will provide. And at the end of the day, your input will tell us how low NIST needs to go on the y-axis. And at what frequency, right? Okay, let's go ahead, next slide. So it sounds incredibly far-fetched to me that NIST is even able to deliver an SRM on a really short timescale. And we've had a lot of lucky breaks along the way. And we actually have, at this point in time, 7 prototypes for an SRM wafers. And that SRM wafer has 2 coupons on each wafer. And I think this is a 4-inch wafer that you're seeing on the left. And so what you see on the left in that picture is Lucas is holding one of these SRM wafers in his hand in the clean room. And you can see in the top right of the picture, you can see a GDS file of the picture. So that's a layout file of the picture of the wafer. And then on the right, you can see a coupon labeled FS2. And I think Mike Hill took that picture. And on the far right, you can see a top view stitched image of an on-wafer calibration kit. So what I've told you so far is absolutely true. NIST is going to develop an S parameter, a materials characterization coupon that you can stick hopefully in your cavities or whatever technique you're using to measure the permittivity. NIST is also developing on-wafer calibration kits that may go along with those coupons, so that when you apply your calibrations to your integrated circuits or whatever your applications are, your antennas, you can also do NIST traceable on-wafer calibrations, which would be a first ever thing that NIST would provide. So the right-hand side, I think, is something that will happen down the road and maybe a spin-off for a future iNEMI project. And I think there are other future iNEMI projects that I could see you leveraging this standard reference material. So like power, for instance, microwave power is really important on chip for integrated amplifiers, if that's your industry. You could also envision coupons for characterizing thin films, like if you're in the paint industry and you're making materials that go on bumpers, you need to know their electrical properties for millimeter wave radar. We're going to work on that. But what we do next needs to be influenced by what industry needs. So if you participate in one of these activities, or if you talk to us, you can help guide what NIST does next and how that impacts the types of traceability that we're able to provide. Go ahead, next slide. Okay, so what does success look like? So the thing on the left is where we are now. We have no traceability for dielectric constant or loss tangent, period. That has tremendous impacts for on-wafer microelectronics. There are no traceable S parameter measurements of RF power, antennas, liquids, polymers. All that stuff on wafer has not been characterized and is not traceable. On the right is what can happen after this iNEMI activity. We can deliver a standard reference material that can serve as a platform for S parameter, power, antennas, liquids, polymers, all those traceability needs that you guys might have. We might be able to answer if we have the standard. And so that's really important. And what we do next will be impacted by what you say. It matters to you, right? Go ahead, next slide. Okay, so here's my dream, right? My dream, or Ermi's dream, or Mike's dream, for that matter, is that Mike goes to the NIST website, types in dielectric, and there's SRM42, because it's the answer to everything. And you have an ultra high purity fused silica dielectric constant and loss tangent from 1 gigahertz to 1 terahertz. And that's your traceable standard reference material right there. Okay, go ahead, next slide. Okay, so with that, I'd like to open the floor for questions. Hopefully I'm not too over time, and I'd love to answer your questions and get your feedback on things that we need to consider when we're doing this, and whether or not you're interested in it.
Yes, thank you very much, Nate. Really, really nice presentation. And Mike, I don't know if you had anything to add. In the meantime, I'm going to go to the chat window and ask for people to put in their comments in there for any of the questions for Nate and Mike, as well as myself, in terms of either the technology part of it, the timeline, any other questions. So, Mike, do you want to add anything to the presentation or to the overall talk today?
Not really. I mean, I think Nate did a really good job of covering the project. There's a couple of questions that came up in the chat. I've been trying to answer them, at least from my perspective. I think there's one that I'd like to have you comment a little bit on, Ermi, with respect to the funding of the iNEMI projects. There was a question related to how they're generally funded, and I think my explanation was that, at least in the ones that I've been involved in, it's sort of a volunteer basis for the iNEMI participants. But I wasn't sure if there are other funding methods that have existed for different iNEMI projects. And maybe you'd like to comment on that.
Okay. Yeah, great. No, I didn't realize that you were answering all the chat. Multitasking is always the value of of any iNEMI project or any other project. So thanks, Mike. We can think everybody can see the chat. So in terms of the project funding, basically it is the fundamental requirement is that your company has to be a member of iNEMI. So that I just want to make sure that is clear. The membership levels, if your company is not a member, then we can talk about it. Just contact me offline. We have different types of memberships available. Once your company or your organization is part of iNEMI, already a member, then you can participate in as many projects as you want, and that's what Mike said about voluntary. So you can be the driver of the project, in which case you or your company, in which case you spend your time in basically scoping out the project, really understanding and leading the project. That requires a fair or larger amount of your time commitment, but in theory you get more more out of it, because you get the results that you and your company want. There are the other types of participation where you're not necessarily actively driving the project, but you are contributing to the project by doing some experiments and or attending the project reviews and participating in the discussions, and by that driving the project. So hopefully that answer is clear in terms of the participation in iNEMI projects. So this discussion about eliminate radiation loss during measurements, maybe we can just, I actually don't know, to be very honest with you. I don't know how the Q&A on chat translates to the recording. I honestly don't know. So, and since a lot of the people who registered, are in Asia, and we're only having one call for participation, I think any key discussion maybe we should at least verbally answer. So, Nate, this discussion about the radiation. Yeah. Go ahead and answer it verbally.
So I think the question was about how can you eliminate radiation loss during measurements? That is a very complex question. Jobin, can you tell me a little bit more if you are talking about radiation in the cavities or radiation for on-wafer measurements? if you're still on the line.
I don't think the participants can unmute, and
Okay.
I
Oh, they can't
don't.
unmute. Okay. I
No.
will just answer both questions.
Yeah.
So I think for the so I think radiation in the cavities is a complicated question, but the way that we kind of account for it is by in the mode matching math that's used to characterize the SCR cavities. So that's one of the nice things about the SCR theory is that it's relatively well developed, and it allows you to include higher order modes that can propagate in the sample when you split the cavity apart, because there's no continuous conductor boundary condition, because you have opened up the cavity to stick in this sample, and there's some metal flange that's around the cavity itself, right? And so what you do is you say that there's a boundary condition there, and you include higher order modes, and the higher order modes influence the resonance frequency that you measure with the SCR cavities. So that's one answer if that was his question. The other answer is how do you eliminate radiation loss during your measurements of on wafer measurements, right? That's the other way to interpret that question. So radiation on wafer is actually a really, really complicated question. And some of the best work on that particular subject was done by Wolfgang Heinrich in the early 2000s and late 1990s. So in that work, they started to understand the impact of surface roughness of the metal and how that impacts radiation. They also in the late 2000s and in 2018, Wolfgang started to study the impacts of the slab mode that can propagate on the wafer and cause interactions from device to device, and that can impact the radiation. In fact, that's the dominant source of radiation for many on wafer measurements. And so the answer to your question is really a compound answer. So first off, you can eliminate it in some cases by adding a high dielectric constant substrate. If your material, if the chip on which you fabricated your on-wafer electronics is relatively thick, around 500 microns thick, and your ground-to-ground spacing of your CPW is like on the order of a couple hundred microns, right? So in that instance, you would just add a high dielectric constant material underneath your chip that you're measuring. The other answer is that if your material is really, really thin, right, as they are with many new 3.5 compound semiconductors, in that instance, you might actually want to put an air chuck below your sample because the slab mode cutoff frequency is so high that if you have the metal below the chip, that will create a sort of a waveguide effect inside the substrate, and that will also lead to radiation. So in that instance, you might want to have an air chuck. In the case where you have there's other types of radiation impacts, and those other types of radiation impacts can be due to the fact that you didn't land your probes symmetrically, right? So if your probes are slightly biased to one ground plane or another, that can lead to other types of higher order modes that propagate in your CPW and lead to radiation. Right now, NIST is this is the first time I told anybody this, but we're doing some experiments where we are doing a ground plane sweep wafer. So in that wafer, we have one of these fancy mosaic wafers, and we have, or maybe I think actually it's sapphire. In that particular case, it's sapphire, and we have a bunch of calibration kits that are all optimally designed, and we varied the ratio of the center conductor width to the ground plane width, but kept the characteristic impedance of the CPW the same. And that would allow you to understand how geometry impacts radiation. On that same wafer, we've actually fabricated another wafer on the other side where the material is rough, right? Because there's often some confusion in the literature is this radiation that you're seeing due to the geometry of the electrodes? Is it due to the slab mode, or is it due to the roughness in the electrodes? And so that experiment would test that. So that's an identical layout. It's just fabricated on the rough side of the sapphire wafer. So I think the answer to your question is really complicated without additional information. Could be cavities, you know, then it's just mode matching takes care of it. If it's on wafer, probably you want to make sure that your probes are centered. You might want to use a high dielectric constant chuck. I think that answers your question. Is that a good answer to everyone's satisfaction?
I think that's a good start.
Yeah, my eyes glazed over, but other than that, it was very good. No, it was very excellent. By the way, I've also figured out how to unmute somebody if I can find him. This was good. Any other questions before we close? By the excellent presentation, and thanks to Mike also for responding to the chat messages. So we've covered most of the messages, questions that have come up earlier. Anything else that we'd like to, anybody want to hear before we wrap up the discussion?
Ermi, just as a logistics thing, do you want to go back to the slide on how to contact you for getting involved?
Sure.
Just so that you can copy that down if they are interested.
Thank you. Thank you so much. You will all get the notes, not notes. What's the word? The presentation material, and I will include the contact information there. But you could copy it down as well as in a week's time you would get the information, the slide deck. Okay, so if no other questions, again, thank you all for your time. Thanks to Nate and Mike for the excellent preparation and presentation, all of you for your time. And I'm really hoping that most of you would be able to join this project. As Nate and Mike mentioned, we've already started doing a fair amount of the background work and initial feasibility studies, part of the previous project. We also have a active core team. You can join the project, be part of the core team, or be the part of the extended team. And any questions, you can contact me. Thank you again for your time. I'm going to log out now and wish you all